Let's look at some theorems about the continuity of functions formed by combining two continuous functions in various ways. First, we have the sum of continuous functions theorem. This states that if f of xy is continuous at a point x naught, y naught, and if g of xy is continuous at that same point, then the sum of the functions is continuous at that point. Next, we have the product of continuous functions theorem. This rule states that if a function g of x is continuous at a point x naught and h of y is continuous at a point y naught, then the product of the function f of xy is continuous at the point x naught, y naught. Finally, we have the composition of continuous functions theorem. Suppose we have a function g of xy that is a continuous function at some point x naught, y naught, and z naught is equal to g evaluated at x naught, y naught. Then let f be a function such that z naught is in the domain of f and that f is continuous at z naught. Then the composition of f and g is continuous at the point x naught, y naught. Here we are asked to show that the function f of xy equals the cube root of the quantity x squared y is continuous everywhere. Instead of looking at this as a single function, let's break it apart. Notice that this is equivalent to the composition of a product of functions. If we let g of x equal x squared, then h of y is y. We know that both x squared and y are continuous for all real numbers, so by the product of continuous functions theorem, g of x times h of y is a continuous function. If we let j of xy equal x squared y, we see that j of xy is continuous everywhere. Comparing f of xy to j of xy, we see that f is the cube root of j. We know that the cube root function is continuous for all real numbers, so if we define k of x as the cube root of x, we can compose k of x and j of xy to get f of xy equals the cube root of the quantity x squared y. Therefore, by the composition of functions theorem, we know that f of xy is continuous everywhere because j of xy and k of x are continuous for all real numbers.